y'all. Darley Berry Jr. here, a bit earlier than planned. So I'll go to about 20 minutes after the hour. And as promised, we'll do some centripetal force problems, looking at the university physics textbook. So I'll read through it until we get to the examples, and we'll see what they're talking about. So we have 6.3 centripetal force. By the end of this section, we'll be able to explain the equation for centripetal acceleration, apply Newton's second law to develop the equation for centripetal force, and use circular motion concepts in solving problems involving Newton's laws of motion. In Motion in 23 Dimensions, we examine the basic concepts of circular motion and the object undergoing circular motion, like one of the race cars shown at the beginning of this chapter, must be accelerating because it's changing the direction of its velocity, which we discussed in the previous video, last video, or the one before. We proved that this centrally directed acceleration, called centripetal acceleration, is given by the formula centripetal acceleration equals the tangential velocity squared over the radius of the centripetal acceleration, where v is the velocity of the object directed along the tangent line to the curve at any instant. If we know the angular velocity, omega, then we can use, that's interesting. That's on the formula sheet as well, thinking about it. So the centripetal acceleration is the radius times the angular frequency, the angular frequency squared. And you can remember that we can multiply this over and say v squared is r squared omega squared. Angular velocity gives the rate at which the object is turning through the curve in units of radians a second. This acceleration acts along the radius of the curved path and is thus also referred to as radial acceleration because it's pointing directed to the center. An acceleration must be produced by a force. Any force or combination of forces can cause a centripetal or radial acceleration. The three examples are the tension in a rope on a tetherball, the force of Earth's gravity on the moon, friction between roller skates and a rink floor, a banked roadway's force on the car, and forces on the tube of a spinning centrifuge. Right? So basically they're looking at it like acceleration equals force over mass. In order to have an acceleration, it must be a force. So I use the example of the Earth-Moon system, where the force of gravity is causing the moon to revolve around the sun, revolve around the Earth. So because there's an acceleration, a change in direction of the moon, there must be a force that's causing that mass to accelerate. And the magnitude of that acceleration will be the magnitude of the force divided by the mass of the object. Acceleration must be produced at that. Any net force causing uniform circular motion is called a centripetal force. So if it's uniform circular motion, it's a centripetal force. The direction of a centripetal force is towards the center of curvature, the same as the direction of centripetal acceleration. According to Newton's second law of motion, net force is mass times acceleration. So I can add the net there. For uniform circular motion, the acceleration is centripetal acceleration. A equals AC. Thus, the magnitude of centripetal force is FC equals MAC. By substituting the expressions for centripetal acceleration, we get two expressions for the centripetal force Fc in terms of mass, velocity, angular velocity, and radius of curvature. So F equals MAC equals mv squared over r equals mr omega squared equals uh, equals mv squared over r. So I mean, these two, these ones seem to be the foundational formulas. And from there, we can plug things in. You may use whichever expression for centripetal force is more convenient. Centripetal force is always perpendicular to the path and points to the center of curvature because AC is perpendicular to the velocity and points to the center of curvature. Note that if you solve the first expression for R, you get R equals mv squared over FC. Okay. This implies that for a given mass and velocity, a large centripetal force causes a small radius of curvature. Makes sense? That is a tight curve. The more it's pulling in, the smaller the curve. Makes sense? The frictional force applies to centripetal force and is numerically equal to it. Okay. Now we're talking about what I need to get to is like a car being held by centripetal force. Oh, the, the frictional force is the centripetal force. Let's think about that. So if you have a car that's going around this curve, the acceleration is inward, the FC is inward, and friction is always opposite the force. Like F would be inward, right? Well, I guess it depends on how fast the thing is going. I remember a professor saying that. So if this car is going very slow, let's say the car is going very fast, then friction is inward to stop it from slipping, and if the car is going slow, friction will still be going inward because it's not slipping. I'm thinking about a car on a car is flat, then it's going to always be inward. But if a car is on an incline, and if it's going fast, the centripetal force, the friction is inward. If it's going slow, then it's outward to stop it from slipping down. So these are two different scenarios. One is flat, um, and one is on an incline. So the incline one, the friction can go either way. Frictional force applies to centripetal force and is numerically equal to it. So on the flat plane, the centripetal force is the frictional force. The larger FC, the smaller the radius of the curve, and the sharper the R of R, and the sharper the curve. The second curve has the same V, but a large F produces a smaller R. In other words, a car can go a certain speed, but if you turn the wheel just a little bit, it'll make a big circle. Turn the wheel a lot, it'll make a small circle. All right, so this is now we get into the meat of it. What coefficient of friction do cars need on a flat curve? Calculate the centripetal force exerted on, so you have a 900 kilogram car. The radius is 500 meters, and V is 25 meters per second. So basically we have this scenario here. Copy this down. So this is M, V. Assuming an unbanked curve, find the minimum static coefficient of friction between the tires and the road. Static friction being the reason that keeps the car from slipping. Let's go ahead and duplicate this. So we have the weight of the car, which I always call FG. We have the normal force. Those are equal if the car is not flying away. We have the F equals FC. Inward. And I like how they draw all the arrows on one point. So looking downward, or I guess horizontal. These are going to be equal. I should have just copied the arrow, but try to keep it roughly. And this will be inward. So we have normal force Fg, F equals B. All right. We're simply using this equation here. Fc is mv squared over r. So Fc is mv squared over r. We put the numbers in. 900 kilograms, 25 meters per second squared over 500 meters. So that's 125 newtons of force. So that's also the frictional force, a lot of friction. Figure 6.21 shows the forces acting on the car on an unbanked level ground curve. Friction is to the left, keeping the car from slipping. And because it is on the horizontal, the only horizontal force acting on the car, the friction is the centripetal force in this case. We know that the maximum static friction at which the tires roll but do not slip. Oh, so I missed this piece of information. Max F equals N maximum static friction, which the tires roll but do not slip, is the coefficient of friction times the normal force, where mu is the static coefficient of friction and N is the normal force. The normal force equals the car's weight on level ground, so N equals mg. Thus, the centripetal force in this situation is Sc or F or mu Sn or mu Smg. Some stuff. In other words, the strongest friction is not saying that that is friction, because if the car is turning very slowly, you just have a little bit of friction. But the maximum it can be, I think this is not worded so well. So when it's saying the maximum static friction, it's saying the maximum it can be is the normal force times friction. Now we have a relationship between centripetal force and the coefficient of friction. Using the equation Fc equals mv squared over r, we obtain mv squared over r equals mu Smg. I'll put the max there. That is very important. But I don't know if this was on the formula sheet, but so I'll check now and see. You all hold tight. I shall be right back. Thank you for waiting. I'm looking at the formula sheet. That formula isn't on the sheet, as far as I can tell. So that's just something that I have to hold up. No, it is there. It's written It's written as the magnitude of the friction. No, the magnitude of the friction force is less than or equal to the maximum friction force. That's what that means. So, as I was saying earlier, if the car is going slowly around the curve, the friction force will be less than the maximum. And if it's going quickly around the curve, as long as it doesn't exceed the maximum, it'll not slide away. Once it exceeds the maximum, it'll slide away. So that's possible to calculate exactly how fast you can go around a curve as long as you have the coefficient of friction. So that's pretty neat. So if you're on a curve, a slanted curve, the minimum speed you can go, assuming that if you stop, you'll slide. How do you get the minimum friction? Calculate the maximum, and as long as we don't go fast enough to exceed that, you won't slip up. What we have to do is calculate what that would have to mean is that FG in that direction is already greater than mu n. And we have to calculate how much centrifugal force we need to make up that difference. So I'm just thinking ahead to a problem that I'll be working on in a bit. But that's some interesting stuff. So get a bit of a better understanding. Now we have the relationship between centripetal force and the coefficient of friction. Using the equation Fc was mv squared over r, we obtain mv squared over r equals mu s mg. Just maneuvering these things around. We solve for this mu s, noting that the mass cancels and obtain v squared over rg. Substituting the knowns, because the coefficient of friction are approximate, the answer given is only 2 digits. Significance. The coefficient of friction found in figure 6.21 is much smaller than is typically found between tires and roads. The car still negotiates the curve if the coefficient is greater than 0.13 because static friction is a response force able to assume a value less but no more than mu s, which I deduced or defined earlier. A higher coefficient would also allow the car to negotiate the curve at a higher speed, but if the coefficient of friction is less, the safe speed will be less than 25 meters per second. Note that the mass cancels, implying that in this example, it does not matter how heavily loaded the car is to negotiate the turn. Mass cancels because friction is assumed proportional to the normal force, which in turn is proportional to mass. If the surface of the road were banked, the normal force would be less, as discussed next. All right. Check your understanding. A car moving at 96.8 kilometers per hour travels around a circular curve at that radius on a flat country road. What must be the minimum coefficient of static friction to keep the car from slipping? All right, you might look at that later. First, let's look at banked curve. Actually, this might be where I wrap up here. Let us now consider banked curves, where the slope of the road helps you negotiate the curve. The greater the angle theta, the faster you can take the curve. Racetracks for bikes as well as cars, for example, have steeply banked curves. In an ideally banked curve, the angle theta is such that you can negotiate the curve at a certain speed without the aid of friction between the tires on the road. We will derive an expression for theta for an ideally banked curve and consider an example related to it. Right? So now we have a curve like so. We have theta. This is our car going into the page. And it's interesting to note that this is, what is it just how they do it? I notice I always put my arrows for I always put my triangle for the forces at the bottom. So I might say, for instance, that this is FG and this is FG cosine theta, and this is FG sine theta, and this is also theta, because if this we lift it up to 90 degrees, then this would just fall straight down, and sine of 90 degrees is 1. And conversely, if this was lifted to 90 degrees, cosine of 90 degrees is 0, so 0 of the gravitational force will be going horizontal. And with the normal force, this time going like this, the max F mu n, which is going to equal mu fg cosine theta. So the bigger the angle, the less friction, because there's less of the roll pushing down. Makes sense. So equals equal n. Me in the book, the main thing's a bit different. I'll check to make sure. And this sine theta, or FG sine theta, equals the centrifugal force. See how that equals F net? Oh, I see. It's saying that the speed is such that it is an ideally banked curve, so there's no friction involved. It would just fly away if it wasn't for the friction force pulling it in. It's interesting. For the ideal banking, the net external force equals the horizontal centripetal force in the absence of friction. That's why they do that. I think they're saying FG sine theta is directly to the center. Still a bit confused about this. This arrow here, is that the centripetal force or is it going down? Well, it can't be going, it has to be going level with the circle. So this is an inward directed force. It has to be in the plane. So it must be here. The car on this bent curve is moving away and turning left. For ideal banking, the net external force equals the horizontal centripetal force in the absence of friction. The components of the normal force in the horizontal and vertical directions must equal the centripetal force and the weight of the car. Hmm. Uh, they're breaking up the normal force. That's why they put the angle at the top. Is that goes here? So these are components of the normal force. The mass is going down, so this is what they broke up. The components of the normal force in the horizontal and vertical direction must equal the centripetal force and the weight of the car. So this equals Fg and y equals Nx. Interesting. It's very unusual. In this case, in cases in which forces are not parallel, it is most convenient to consider components along perpendicular axes, in this case the vertical and horizontal directions. Figure 6.22 shows a rebrighted diagram on a frictionless for a car on a frictionless bank curve. Angle theta is ideal for the speed and radius, and then the net external force equals the necessary centripetal force. The only two external forces acting on the car are its weight and the normal force of the road. Those are the two external forces. A frictionless surface can only exert a force perpendicular to the surface, that is, a normal force. There's no friction because it's perfectly on there. These two forces must add to give a net external force. These two forces must add to give a net external force that is horizontal towards the center of curvature and has a magnitude of mv squared over r. V squared over r, which is the centripetal force. Because this is a crucial force and it is horizontal, we use the coordinate system with vertical and horizontal axes. Only the normal force has a horizontal component, so this must equal the centripetal force. Centripetal force must equal Fg sine theta, which is in sine theta. No, just in sine theta. Okay, I still have to work on this. Oh no, it's just in sine theta. There's in at. Thus the car does not leave the surface of the road, the net vertical force must be zero, meaning that the vertical components of the two external forces must be equal in magnitude and opposite in direction. And from figure 622, we see that the vertical component of the normal force is in cosine theta. That's ny. And the only other vertical force is the car's weight. These must be equal in magnitude, thus in cosine theta equals ng. Trippy. So the Fg is just I think I'm mixing a few things up. Fc does equal that. Fc equals that. Wrote too much. Equals in x or sine theta or d sine theta. Not sure how n cosine theta is mg when n is mg. So I need to see what formula they're using for n. Now let me scroll properly. Oh, because I have some of the window on the side there. Of course. So why this thing is excluding to the other screen like that. I'm not sure what I'm clicking to make it do that. All right. Normal force here, a box at rest on a horizontal first focus surface, the normal is mg. Clearly here the normal is different. Or is it just that the normal is bigger? Let's bring it way to the, probably looking a bit farther to the left. For some reason, this thing keeps shooting to the other side. For example, if the crate you try to push with a force parallel to the floor has a mass of 100 kilograms, then the normal force is equal to the weight. So there you go, N equals mg. But here they seem to be saying N is something else. But a normal force here, I guess because what must be happening is the car, since it's going on a curve, the centrifugal force is pushing it against the uh, uh, bank. So in this case, N by itself is greater than mg, and Ny equals Fg. I'll just call it how I normally call it, banked. N is greater than Fg, and Ny equals Fg when you're on the bank curve like that. So I mean that's what resolves it. And Nx equals mg sine theta. All right, so we're going to go with that for the time being. Cosine theta. So Ny equals Fg equals mg equals n cosine theta. So n in this case is greater than Fg because external forces, the centripetal force, is pushing down on the car and making it push on the ground more than its weight alone. It makes sense. So if you twirl a ball around, the pull on your hand is going to be greater than the weight of the ball. Now we can combine the two equations to eliminate n and get an expression for theta as desired. Wow. Right, that's some good stuff. I'll go ahead and call it here. We went over some in-depth concepts of a banked a car going on a bank curve. So I may reiterate some of these principles tomorrow and then extend it to more things and look towards solving any problem I'll need to solve with it. But I actually may have enough to solve it now. I'll see. And but I'll try to keep the weekends busy. Let me know if you have any questions or comments. Like, subscribe if you haven't, and I'll see you next time around.